Hello! This is the third video in Chapter 10 of the Crystal Clear Electronics 2 curriculum. Let's take a look at our next serial protocol, CAN. Adam, do you think I've ever seen CAN before?
CAN, that is Controlled Area Network, is a standard in industry, especially in the automotive industry. If you've ever been in a car or traveled by bus or train, you've probably come across it, as the use of CAN in vehicles has become hugely widespread since the early 2000s. The CAN standard was designed specifically for cars to reduce the number of wires. It was introduced in 1986 by Robert Bosch GmbH after 3 years of development. The last complete standard, CAN 2.0, was published in 1991 and is still the most widely used CAN version. Since then, newer variants have been released, such as CAN FD in 2012 or CAN XL in 2024, but we will not discuss them here. The objective was to develop a reliable, cheap, and simple communication system for the automotive industry. CAN has become so successful that it is widely used in many industrial sectors. It's used in various applications, including road, water, and air vehicles, agriculture, robotics, manufacturing systems, healthcare devices, and even smart homes.
So it's used almost everywhere. I've seen it but didn't know about it. Just from its name, it can be difficult to identify what CAN is, how it works, or what it is used for.
That is why we are here. CAN is a multi-master protocol, so unlike in the general use of I2C and SPI, there is not a single master device and multiple slave devices, but all devices have equal status. These devices are called nodes. Each node has a control unit, or microcontroller, a CAN controller, and a CAN transceiver unit. The microcontroller processes the received data or prepares the data to be sent. The CAN controller acts as a converter between the CAN logic and the logic of the microcontroller, and finally, the CAN transceiver performs the physical layer conversion. The latter contains various additional protections, for example, against overcurrent and overvoltage.
So is there no lower or higher ranking between nodes?
At the CAN protocol level, there is no hierarchy between nodes. Everyone is equal, but there is a priority-based hierarchy between messages of the nodes. Each message has a unique 11 or 29-bit identifier, with the lower values corresponding to higher priority. All messages are received by each node and are processed or ignored according to their own program code.
Does this mean that the message whose identifier is 0 has the highest priority? Why is this the case?
To understand this, first you need to understand how the physical layer works. According to the standard, the CAN network uses a bus topology, so it is often referred to as the CAN bus. Here, the bus does not refer to the means of transport, but to the fact that there is a single common data line to which all devices are connected simultaneously. Any device can initiate a transmission, and all devices can see all messages. Each node connects to this shared data line or bus with the shortest possible stub. The consequence of this is that several devices can start sending at the same time, which is a problematic situation. We will see how the protocol handles this later. Physically, the CAN bus is a pair of wires twisted together. These two wires are called CAN high and CAN low, and the voltage difference between them represents the data. In other words, we call it a differential signal. This design helps reduce the effect of noise and improves the reliability of communication. It also allows signals to reach their destination clearly and without distortion over long distances. For the communication to work correctly, it's essential that a 120 ohm resistor, called a terminating resistor, is connected to each end of the twisted pair. The signals have two states. The logic 0 state is the dominant state, and the logic 1 state is the recessive state. In the dominant state, CAN high is at a higher voltage than CAN low, meaning they have a positive voltage difference. In the recessive state, CAN high and CAN low are at the same voltage. No voltage difference can be measured between them. This means that CAN uses negated logic with a positive voltage representing the logic 0 and 0 voltage representing the logic 1.
And what voltage levels does this mean in practice? Can you give us an example, Adam?
There are no strict constraints, but in the recessive state, the CAN high and low wires are both around 2 to 2.5 volts relative to the ground. The point is that both signals have the same voltage relative to the ground, so their voltage difference is 0. In the dominant state, the CAN high wire is around 3 to 3.5 volts, while the CAN low is around 1 to 1.5 volts. So, the voltage difference between them is usually about 2 to 3 volts. The names are derived from the fact that if one node sends a recessive signal and another a dominant signal, the latter will appear on the bus. The physical layer of the CAN protocol is designed to implement an AND connection between bits sent by multiple devices simultaneously. In the case of the dominant signal, the two wires are pulled apart, while in the case of a recessive signal, they are let go. Thus, if each node gives a recessive signal and releases the bus, the voltage difference across it will be 0, but if even one node pulls apart with the dominant signal, it will be asserted. If there is no communication on the bus, then the potentials of the CAN H and CAN L wires are 0, so the bus is in a recessive state. Priority is also related to this. The lower ID will have 0 bits at higher local values, which will cause the dominant state, so the lower value will be asserted on the bus. Since identical addresses cannot occur by standard, there is no collision during communication. For similar reasons, the idle state is also indicated by the recessive state. This behavior also gives rise to the property that if two devices start sending data to the bus at the same time, the higher priority one will continue uninterrupted, while the lower priority one will detect a collision and stop transmitting.
An example to illustrate this would be good.
Here's an example. Here, we can see a situation where a race condition occurs on the bus. The three nodes start transmitting simultaneously and continue together until the 5th bit of the ID, but node 2 has a higher ID than the others, so as soon as it detects that data other than the one it has defined is on the bus, it stops transmitting and continues as a listener. A similar scene takes place at the 2nd bit of the ID, where the first node detects the change and takes the necessary action. The communication is synchronized, but asynchronous.
It's a bit ambiguous.
Yes, I know. I'll explain briefly. As we discussed in the first video, the fact that the communication is asynchronous essentially means that there is no clock line between the devices and they are not operating on a common clock signal. However, each device operates according to its own clock signal, and it is necessary to synchronize these clocks to ensure that messages are interpreted similarly. The protocol is based on each node sampling the bus at the right time. They can achieve this by having a negotiation at the start of communication at the first recessive dominant transition, this is the start bit, and then at each logical 0 to 1 transition, the participants observe how many standard bit times elapsed. Thus, although the communication is synchronized in operation since it has no clock or other synchronization signal, it is by definition asynchronous.
Adam, what is the speed of CAN buses?
According to the CAN standard, the maximum speed that can be provided by the bus is 1 megabit per second, but there are types that operate at maximum speeds of 5 megabits per second or 125 kilobits per second. All this can be provided with the appropriate termination and within the specified maximum distance.
Could you talk about what CAN messages look like?
Of course. So, the physical layer is now understood. Let's now look at the data link layer. As before, frames are the basis for communication. Within the CAN 2.0 standard, we distinguish between two different types. CAN 2.0a is the basic version, and CAN 2.0b is the extended version. The only difference between the two is the extended length of the ID from 11 to 29 bits. The CAN protocol distinguishes 4 different types of frames: the data frame, the error frame, the remote frame, and the overflow frame. As you can see in the figure, data frames start with the start of the frame bit followed by the message identifier and remote data request bit. The identifier and data request bits are collectively called the arbitration field, and it is here that the priority between the different messages is decided based on which one wins in the arbitration. After 2 control bits, there are 4 bits defining the length of the data, followed by the data, which can be between 0 and 8 bytes, starting with the highest local value bit. One of the control bits is responsible for indicating the extended ID. The other control bit is reserved for further development of the standard. The data length is called DLC in the CAN protocol, which stands for data length code. The data is also referred to as dB, which stands for data bytes. The built-in CRC, which stands for cyclic redundancy check, is the next 16 bits, of which 15 bits are checksum and 1 bit is the terminating one. At the end of the data check, there is a value that is not set by the sending device but is returned by the receiving devices. If an error occurs at the feedback bit or elsewhere, and the device is configured to do so, the sending device repeats the transmission. Finally, 7 consecutive ones indicate the end of the frame. There must always be at least 3 recessive bits between 2 frames. The error frame is simpler and shorter. When any node detects an error, it immediately starts to transmit the error frame, which consists of 2 parts. The error flag, which is 6 identical bits with a value of 0 or 1 depending on the setting, followed by the error delimiter, which consists of 8 ones. The remote frame is very similar in structure to the data frame. The remote data request bit is dominant in it, and there is no data field in the remote frame. That is, data is expected back when this frame is sent. The overflow frame is essentially a version of the error frame with 6 dominant and 8 recessive bits. It can occur in 2 situations. 1, when the receiver requests more time to process the previous data, and the other, when a node violates the time criterion between frames. Since there is no separate clock, nodes set their own clock based on recessive dominant transitions. Because of the importance of frequent synchronization, bit stuffing is used. This means that if 5 bits of the same value appear on the bus, the transmitter inserts a bit with the opposite value. These inserted bits are recognized by the receiver and are not taken into account when the message is evaluated. That is, they are discarded. Of course, if there is an error in the insertion, it is detected by the device. This has 2 huge advantages. One is the possibility to synchronize at most every 5 bit times, as mentioned before, and the other is the possibility to spread error frames. If one of the receivers detects an error, it outputs 6 bits of the same value so that all other nodes on the bus will also signal an error, ensuring that all nodes detect the error.
I think we now have a good understanding of the theoretical aspect of the CAN bus. Can we look at a practical example?
Unfortunately, hobby electronics does not yet use CAN-based solutions very much. The reason is that reading the CAN bus often requires expensive interfaces and software, but less professional, but more cost-effective devices are also becoming more and more common. As I mentioned earlier, it was developed for the automotive industry, which has been using it ever since. Almost without exception, today's cars use CAN buses for communication between the various subunit controllers and sensors. Think, for example, of the throttle response in a modern car. The data from the accelerator pedal sensor is sent via CAN bus to the engine controller, from where the speed, RPM, and temperature information is also sent to the dashboard via CAN bus.
Next time I'm in the car, I'll pay more attention to this. It's strange to think that the vehicle's nervous system is essentially just 2 wires twisted together, and the communication protocol created over 30 years ago can even meet the needs of today's cars.
Well, this is not entirely true. For example, a modern car can have 4 to 6 different CAN buses, but in the premium category, more than 10 is not that rare. Many other communication protocols exist, such as LIN for simple devices and Ethernet for cameras, radars, and other complex driver assistance systems.
This brings us to the end of the 3rd video. Stay tuned for the following video as we delve into the world of USB. Bye!
Bye!